Continuing with our geometric sequences, today we're going to learn how to take the sum of a finite series. The terms of a geometric sequence can be added together if needed, such as when calculating the total amount of money you're going to pay over the life of the loan that charges interest. So this would be like your mortgage loan when you buy a house, or a car loan if you need one to buy a car, right? This is the type of the loan that charges interest, and this is where our geometric series is going to come into play. When a group of terms from a geometric sequence are added together, that group is called a geometric series. There is a difference between sequence and series. The number of terms in that group could go on forever, right? A geometric sequence can go on forever. Or I can limit the number of terms I want and call it finite. So just to be clear, a geometric sequence is basically when you list the numbers in your geometric sequence. That's what we did before. A geometric series, however, is when I take a portion of those numbers and add them together. In this lesson, we will learn different ways to write and evaluate a finite geometric series. First of all, we need to learn summation notation. This is a formula that you will definitely want to have in your notes. I'm going to go through the different parts to it, so hang on just a second. The part on the right should look a little bit familiar to you. A sub 1, or our initial term, multiplied by the common ratio to the k minus 1 power. You saw it before as n minus 1. This is the explicit formula for a geometric sequence. The symbol to the left is called sigma. It means to take the sum of something. So in other words, I'm going to add some numbers together. K equals 1 means that that's our starting term or initial term. N represents the number of terms that we're going to add together. So I would actually say this, take the sum from 1 to n of the series A1 times r to the k minus 1 power. Let me give you a more specific example and show you what that does for us. So here I have an actual geometric series in here. I have an initial term of 2 and a common ratio of 3. So if I were to actually write out this sequence, I would put, I start at 2, right, and multiply by 3 each time, so I have 2, 6, 18, 54, and so on. That's called expanding the sequence. So if you're asked to expand the sequence, it means to simply write out the numbers of your sequence. If I'm asked to evaluate the series, that's different. Notice how this says from where k equals 1 to 4. That means I'm going to add together the first 4 terms of my series. So I'm going to take the first 4 terms of my sequence, 2, 6, 18, and 54. I'm going to add them together, and I'm going to get a total of 80. 80 is what I get when I evaluate the series. This is a great method for when you only have a few terms to add together, like maybe up to 4 or 5, maybe even 6. But what if I had to find the sum of the first 100 terms, or 1,000 terms, or sometimes even more than that? That would be a problem for me if I had to write out all those numbers and add them together. So of course, there's another way when I have too many terms to add them all together. So just a quick side note, if you were asked to add all the terms of a sequence together, that's called an infinite series, since our sequence is infinite, right? An infinite series we're going to look at next time. Remember, this time we're looking at finite series, or a series that ends. So here's a different way to look at that summation formula, right? This is the same thing, just looks a little different. So S stands for sum. N is the number of terms we have to add together. So if I put a 5 here, that means I'm taking the sum of the first 5 terms. A sub 1 is the initial term or starting value. R is still the common ratio. And then I have another N over here for the number of terms. So with numbers in it, this is the same series that I had to add together just a second ago. I have an initial value of 2, a common ratio of 3, and I want to add together the first 4 terms. So I simply put those numbers into my formula, and now I can multiply it out. First thing I want to do is to do the exponent, right? 3 to the 4th power is 81. Then I'm going to do what's in the parentheses. I'm going to do the subtraction in the denominator at the same time. I'm going to multiply 2 times negative 80. And then I'm going to do the division, negative 160 divided by negative 2. And I still get 80. That's the same answer that I got when I simply wrote out those 4 terms and added them together. So still easy enough when I've only got 4 terms. What if I have to add the first 15 terms together? So here I have a different geometric sequence, and I want to add its first 15 terms. So I need to identify some of our values, right? I need to know N, A sub 1, and R. Those are my missing values that I'm going to need from this sequence. So A sub 1 is 1. My common ratio is 4. And N is 15 since I want to add together the first 15 terms. When I put those into my formula, first of all I'm going to do 4 to the 15th power. I'm going to take 1 minus this more than 1 billion number. 1 times that number won't change that number, so then I'm going to divide it by negative 3. And I get over 357 million. That would be pretty hard if I had to write down all 15 terms and add them together. But with the formula and manipulating it in just the right way, it's not a bad problem. So when is this used? We kind of already talked about that, right? The summation formula of a finite geometric series affects everyone who makes a payment on a loan, whether they know it or not. So we're going to go through one quick example on how to actually use that formula in an actual loan setting. So this is kind of that same formula, right? Only it looks a little different. This is the formula that banks and lenders use when they use this kind of loan. So let's say that Celine is applying for a $10,000 college loan to be repaid over 10 years. Her APR, which is percentage rate, on the loan is 3%. However, the interest on the loan is compounded monthly. That means that she pays interest every month. So we're going to take that 3% and we're going to divide it by 12 to find her monthly percent. The amount Celine will owe can be found using this formula for the sum of a loan. P stands for the principal amount. That's the original amount that you borrow. A is the monthly payment amount. That's the amount that you have to pay to the bank every month. I is the monthly interest rate on the loan, so the 3% divided by 12. And N is the number of monthly payments. So again, here's our summation formula, right? The sum of the first n terms from where k is 1 to n. So if she's paying over 10 years, we're going to have to calculate that in number of months. So our original loan amount or principal was $10,000. Her monthly payment amount we don't know yet, so we're going to call that X. Her monthly interest rate, again, we're going to take that 3% and divide it by 12, which gives me 0.25%, which is a decimal, is 0.0025. The number of monthly payments over 10 years is 120 months. We're going to use this formula to find Celine's monthly payment amount. So inside the parentheses, we have a little mini formula in here, 1 over 1 plus the monthly interest. If I put in my 0.0025 that we calculated, I would get 0.9975. That's actually going to be my common ratio. So now let's change this into our sum equation or summation formula. I'm going to take all of this information, my principal, my monthly payment amount, my common ratio, right? And we're going to change that into our summation formula that we used before. Remember that n is the number of payments, so that's going to be 120. A sub 1 is our initial amount, and R is going to be our common ratio. So let's take a look. The summation amount is $10,000. That's how much she is going to pay. That's not the total amount she's going to pay back, but that was her initial amount. A sub 1, in this case, in a loan case, is her monthly payment. We don't know that yet. And 0.9975 is her common ratio. 120 is the number of months. To solve that, I'm going to have to do the same thing I did before. Do the exponent part, 1 minus that number, right? And in the denominator, 1 minus 0.9975. I'm going to multiply the denominator to both sides and then divide by whatever I get in the parentheses. We'll go over that some more in class. But when I solve this, I get a monthly payment amount of $96.34. That means that that's the amount Celine has to pay to her bank every month to repay that $10,000 student loan. And at the end of 10 years, she'll have it paid off. She's going to end up paying back way more than $10,000. In fact, if I multiply that $96.34 by 120, I find out that to the bank, she's going to pay back a total of $11,560.80. So she pays back over $1,500 in interest for her $10,000 loan. We'll do a couple more of these examples in class, so no stress right now. Just please make sure that your example's written down. Write down whatever questions you have right now, and I'll see you in class. Have a great day.